Good morning. This is Grand Rapids Community College's calculus class, and we are still hoping to connect with Byron Center High School. And right now we haven't yet connected. Last night's homework included trig substitutions to solve integrals, and today we're going to talk about how to do partial fractions for rational polynomials as another integration technique. But I'd like to start with any questions from homework on the trig substitution. And Eric, I think he said number 7. Is that the one you want to look at? Okay. I'm in the wrong section here. Still looking for. Okay. Taylor's here. I don't think I have the test thing. Okay, so this is the reason we think of this as a trig substitution form is this square root function here. And because it's a constant minus x squared, this is going to be the inverse sine, the sine idea. Because r squared minus r squared sine squared theta becomes r squared cosine squared theta, and we can work with that. So square root of 25 is 5, so I'm going to let x equal 5 sine theta. So, and I'll step through it this first time. So x squared is 25 sine squared theta. 25 minus x squared then becomes 25 minus 25 sine squared theta, which you can factor the 25 out and then replace 1 minus sine squared with cosine squared. So the square root of 25 minus x squared becomes 5 cosine theta. And again, normally, good morning out there. It looks like we're going to connect. Normally you'd have absolute values around this, but because inverse sine is restricted to the first and fourth quadrants, cosine's always positive in those quadrants, so we don't need to put those in there. And lastly, back up based on the top, the derivative of x is going to be 5 cosine theta. But this again isn't based on the algebra work here, it's based on looking back at the first substitution. So we're going to substitute this part is going to be dx. This part, the 5 cosine theta here, is going to be the square root of 25 minus x squared. X squared itself is 25 sine squared theta. So I get the integral of 1 over sine squared theta cosine theta with the 5 and the 25. Cosine theta d theta. Okay, so the 5 cosine thetas are going to cancel, and I end up with 1/25, so I'll pull that out, times the integral of cosecant squared theta d theta. Now, normally we don't deal much with cotangents and cosecants, but let me go as an aside here. Cotangent theta is cosine theta over sine theta. So the derivative with respect to theta of cotangent theta, and I can use the quotient rule here, it's going to be the derivative of cosine, which is negative sine, times the denominator, which is sine, minus the derivative of the denominator, times the numerator, all over the denominator squared. And this negative sine squared theta minus cosine squared theta over sine squared theta, which is negative 1 over sine squared theta, or negative cosecant squared theta. The sine squared plus cosine squared that you get if you factor the 1 out of the numerator. I guess I should do that, huh? Becomes 1. So basically what I'm saying is the derivative of cotangent is cosecant squared with a minus sign on it. Similar to the derivative of tangent secant squared, derivative of cotangent is going to be negative cosecant squared. So here we're taking the antiderivative. So this is going to be negative 1 over 25 times the cotangent theta plus c. Now, to find cotangent theta, my recommendation often with these, x over 5 is equal to sine theta. And I tend to draw a little right triangle here. And I'll put theta here with a right angle. Sine is opposite over hypotenuse, so I'll just make the numerator be the opposite side and the denominator the hypotenuse. And then use Pythagorean theorem to find this third side. So in this case, the third side is going to be 25 minus x squared. The square root of 25 minus x squared. Once I do that, then I can figure out cotangent theta. So cotangent is adjacent over opposite, so it's going to be the square root of 25 minus x squared over x. So I mentioned last time, and I'll mention it again, you get a crib sheet. This may be one of those times when you really, really want to take some time putting it together. So especially any kind of trig substitutions, trig identities, derivatives. So for instance, derivative of cotangent is negative cosecant squared. Might be one of those ones you want to put on there just in case. I can't tell you what's going to show up on a test, but anyway, something like this where you explain how to take, if given a trig function, trig identity, you can find the other 6 trig identities, that kind of idea. Other 5, other 6. What do you think, Eric? Is this okay? Was this integral?
I just didn't put cosecant squared.
No, he left it as 1 over sine squared. And then you have a little, it becomes a little bit more difficult to do the derivative of that. You're going to need to multiply it by something like cosine over cosine in order to get the derivative. What would I do with that? Yeah. Okay. Was there another one from homework? Can you say that again? 13? Okay. Okay, so this case, instead of a constant minus x squared like last time, so I use the sine as my trig substitution. In this case, it's the x squared minus the constant. So we're going to use arcsecant because we know secant squared minus 1 is tangent squared. So x, again, we need to figure out how to deal with a 9. So square root of 9 is 3, so x is going to be 3 secant theta. I guess I'll step through this. These steps, you don't have to write all these steps down. There's ones in here, but for a while it might be helpful for you guys to see them. So x squared is 9 secant squared. X squared minus 9 becomes 9 secant squared theta minus 9, which then you can factor out secant squared theta minus 1 and replace that with tangent squared theta. So then when I have something like the square root of x squared minus 9, it's 3 tangent theta. And again, at secant theta, the inverse secant theta is restricted to first and third quadrants. So tangent's always positive in those spots. And one other thing, again, based on the top one, the derivative of both sides there, so dx is going to be 3, and the derivative of secant theta is secant theta tangent theta. Okay, so the top is the square root of x squared minus 9. That's going to be 3 tan theta. Dx is going to be 3 secant theta tangent theta d theta. I haven't really solved for x cubed, but x is 3 secant theta, so I'm just going to cube this part for there. So it becomes the integral, or antiderivative, 3 tan theta on top, 3 secant theta cubed on the bottom, and then 3 secant theta tangent theta d theta for my differential. Are we okay with that? And then this is the 3's become 9 on top, the 3 cubes 27 on the bottom, so I end up with a 1/3 that I can pull out front. I have tangent squared on top, secant over secant cubed, which gives me a secant squared on bottom. Of course, tangent sine over cosine, secant's 1 over cosine, so this becomes sine squared. Let me do that over on the side here for a second. So that's where we get that one from. And then to do the sine squared, this is one of those ones where that you might want to write on your note sheet. Sine squared or cosine squared, we're going to use a double angle formula. This becomes 1/2 of 1 minus the cosine of twice the angle. So I get 1/6. Is 1/3 times 1/2 is 1/6. Antiderivative of 1 times d theta is just theta. The antiderivative of cosine of 2 theta is sine 2 theta over 2 plus some integration constant. Now we have another little identity here. sine 2 theta is 2 sine theta cosine theta. So this becomes 1/6 theta. My 2's are going to cancel. Minus sine theta cosine theta plus c. So now again, I'm going to use a right triangle. Secant theta is x over 3. Secant is hypotenuse over adjacent, so the numerator is going to be hypotenuse, the adjacent is going to be the denominator, and then you use Pythagorean theorem to find the other side. So the opposite side is the square root x squared minus 9. Sine is going to be the square root x squared minus 9 over x. Cosine is going to be 3 over x. Theta itself is just going to be the inverse secant, or arcsecant of x over 3, and sine was the square root of x squared minus 9 over x times cosine is 3 over x plus some integration constant. And there you go. Now again, if you wanted to distribute the 6th, you could probably get rid of that 3 and you could have an x squared on a denominator, but this is fine the way it is. So. Is that okay? Okay. Any more? Another one?
22.
22. Okay. You guys did a good job of hitting all 3 of the different trigs, like substitutions. So we had in the sine, when it was a constant minus x squared, we had secant when it was x squared minus a constant, and now this one's going to be the tangent theta because it's x squared plus a constant. So x is just 1 in this case, so x is going to be tan theta. So that this now, again, eventually I'm not. If you guys want me to, I can go through it again, but square root x squared plus 1 is just going to be secant theta then, and dx is going to be secant squared theta d theta. Again, to get this one step, you can go through the different steps. X squared is tangent squared, x squared plus 1 becomes tangent squared plus 1, which is secant squared, and then we take the square root of that, you get secant. So this becomes the integral from x equals 0 to x equals 1 of secant theta times secant squared theta d theta. So this becomes the integral x equals 0 to x equals 1 of secant cubed theta d theta. So now we had section where we did some trig integrals. If we had secant to even power, we were supposed to, and tangent to any power, we were supposed to pull out a secant squared and figure out the other part in terms of tangent. If we had a secant with a tangent, we were supposed to pull out secant to an odd power with a tangent. We were supposed to pull out secant tangent. I mean, if tangent was the odd power. But this one isn't either of those two situations. So how are we going to integrate secant cube theta? Well, let me back up to this one. So what would be another possible way to try to do the antiderivative of this one?
Tried to do it by parts,
But you didn't get anywhere.
but
So if we try parts, there's two different ways to try this. U could be, well, essentially we want to let U be the secant theta, and dV be secant squared theta d theta. This becomes tangent theta, and du becomes secant theta tangent theta. So then this integral becomes uv, or d theta there, sorry. This d theta should be over here. Minus v du. So I get secant theta tangent theta minus tangent squared theta secant theta d theta. Is that where you got to? So we could choose u equals tan theta and dv is equal to secant tan theta, secant theta tangent theta, and go one more time that way. But that probably would get us back where we started. On the other hand, we could try substituting for tangent squared and see if that gets us anywhere. So tangent squared is secant squared theta minus 1. So I have the integral of secant cubed on the left side, and secant theta tangent theta minus integral of secant cubed theta d theta plus the antiderivative, the integral of secant theta d theta. So this looks like it's going to be one of those ones where I'm going to want to add this integral over to this side because they're identical. And by adding over here, I'm going to end up with 2 times the integral I'm interested in. Antiderivative of secant is the natural log of secant theta plus tangent theta. And then I'm going to divide everything by 2. integration constant. And since you don't know what the constant is, divided by 2 doesn't change the fact that it's an unknown constant. So, hey, nice to see you. Was it okay?
Fourth step, like when you went, yeah, from there to the next step.
Secant squared times secant is secant cubed.
Yeah.
And negative negative gives me positive. 1 times secant theta is, and I just separated out the two pieces of this antiderivative here.
Okay.
And it turned out that when you do that, this integral is the same as the one you started with. It's just the opposite sign. So then I'm going to add this over to the left side and end up with twice the integral I started with.
So if that was a plus, the same
It would have been.
integral as a
It means I was going around in circles. If that had been a plus sign, when I tried to subtract it to the other side, everything would have canceled and I wouldn't have gotten anywhere. But occasionally, that's what happens when you try different techniques. I'm trying to see if they actually gave you anything about secant to the third power. Now, in your book, if you get stuck on one and you want to go back, we're going to talk about this next class period using the integration tables. Instead of calculators, I had to buy the book called the GRCC manual for a lot of money, twice what a normal textbook cost. And it had hundreds and hundreds of integral tables, and we would just go look for them instead of having a nice calculator do stuff. And so they would have formulas like this that you would look up. So here you can see the antiderivative of secant cubed is here, 1/2 secant tangent plus 1/2 the natural log of secant plus tangent plus c, which is what we came with. And then much of my class became trying to derive all the formulas in the GRCC manual. That was sort of the class, by parts or by whatever technique we were trying to prove all those different formulas. But it ends up being the same thing. Is this okay, Eric?
yeah.
So now I need to go back to where I was here. Antiderivative of secant cubed, we've said now, is 1/2 secant theta tangent theta plus 1/2 the natural log of secant theta plus tangent theta. And instead of plus c here, we're going to be evaluating from x equals 0 to x equals 1. And all we have to do now is figure out what secant theta and tangent theta are in terms of x, but we have them both here. So I get 1/2 secant times the tangent plus 1/2 the natural log of the secant plus the tangent. And this is all evaluated from x equals 0 to x equals 1. So when I plug in x equals 1, I get the square root of 2 times 1 plus 1/2 the natural log of the square root of 2 plus 1 minus what I get when I plug in 0, which is 1/2 the square root of 1 times 0 plus 1/2 the natural log of 1 plus 0, which is still 0, so this whole right side goes to 0. So I have the square root of 2 over 2 plus 1/2 the natural log of the square root of 2 plus 1. And maybe your calculator, your computer book might have the answer where you put this half as a power inside and you end up with a square root of the square root or something, but this is essentially the answer. Okay, but this is where you got stymied trying to antiderivative differentiate the secant cubed. Okay. That was good though. We did all three different substitutions. So. There was one other even number problem that I suppose I want to give a hint if you want to try and do it. Oh no, actually it was the odd problem. It was this one here. Let 0, 0 be the center of the smaller circle, the way it's drawn, although you don't really know that it's the smaller circle. But because you know that's at a right angle there, it makes it easier to figure out the limits on your integral. So you're going to want to have your origin be there, or at least on that axis. Okay. So if you're trying to do that one, that's my recommendation.
You should have your origin be on.
Where the center of the blue circle.
Okay.
The one that you know is at the same axis as the point of intersection. The way they've drawn it. If you make it down here, it makes it very difficult to find the coordinate for where those two intersect. It makes it ugly, actually. It's doable, but it's not a very pretty integral. I mean, limit. Okay. So we have one more major integration technique. This one's called partial fractions. And it's based on an idea from quite a while ago in algebra. So in this case, we're looking, so for the trig subs, we were looking at square roots of functions where it was x squared plus 1, or 1 minus x squared, or x squared minus 1. In this case, we're looking at trying to find integrals of rational polynomials. So we're looking at antiderivatives of rational polynomials, and again, we're talking real valued. We're going to restrict ourselves to real valued coefficients. And there's two things I want to say. If the degree, which I don't know that I assigned any of these, but it's if the degree of your numerator is greater than the degree of your denominator, then divide them. Into the form, I believe your book uses this. Where S of x is a polynomial, and R of x is a polynomial that's of lesser degree than Q. So either we're going to start out with a rational polynomial where the degree in the numerator is smaller, or if it's not, we're going to divide it out until the rational polynomial is, and we can integrate polynomials. We just use the exponent rule, x to n over n. But that's kind of the first step. If for some reason you're given a rational polynomial where this degree is higher than this one, divide it by longhand. And you can, in this section, I don't mind if you use your calculator to divide that. It'll divide it out and simplify it for you. Okay. So The theorem that we're actually basing all this on is the theorem from algebra that says every polynomial with real coefficients can be factored into the product of linear terms and irreducible quadratic terms. That also have real coefficients. And we'll stop there. So what that means is Q of X can be factored. Into factors like ax plus b or ax squared plus bx plus c, where this quadratic can't be reduced any farther. And this is essentially going to be our first step. We're going to have to factor this on there. Now, a lot of them are actually going to be in factored form, but some of them aren't. Okay. So we're going to have 4 cases. Case 1, all going to be linear factors. None of them are repeated. Case 2, they're all going to be linear factors. And some of them might be repeated, not necessarily all. Case 3, there might be some quadratic factors. None repeated. And then finally, case 4, there's some quadratic factors, and some of those might be repeated. So these are the linear factors. So the first case, everything's a linear factor. Second case, everything's a linear factor, but some of them might be repeated. So you might have x squared or x plus 1 squared. That's what I mean by repeated factor. Case 3, there's a combination of linear and quadratic factors, but none of them are repeated. And then case 4, there's a combination of linear and quadratic factors, and some of them might be repeated, even the quadratic ones. Okay. So I have the integral, say, of x squared minus 5x plus 6. So the first step is to factor that denominator. In this case, it's x minus 2, x minus 3. And the idea is I should be able to take 1 over x minus 2 times x minus 3 and rewrite it as something over x minus 2 plus something else over x minus 3. And this part of it, which actually is some of the more difficult algebraic part, isn't really part of the calculus, but we're using this idea. You may or may not have spent much time doing this in your, if you took college algebra, you probably spent some time with this, but maybe not in a pre-calc class. So if I multiply everything by the common denominator, x minus 2 times x minus 3, on the left I get 1. Let me go ahead and write it out here. And on the right I get a times x minus 3 plus b times x minus 2. Now there's a couple different ways to solve these, and over the time we're going to spend today, I'm going to do it both ways. Because sometimes one works better than the other. So one way to figure out what a and b have to be is to just substitute in. Now you notice, if I let x equal 3, what's going to happen to this x minus 3 term? It's going to be 0. So I have 1 equals a times 0 plus b, and if x equals 3, I get b times 1. So b is just 1. Thinking that same idea, what if I want to cancel the b out and figure out what a is? What would I let x equal? Yeah, let x equal 2. Then 1 is going to be a times 2 minus 3, which is negative 1. This part's going to go to 0. So 1 equals negative a. So a is negative 1. Okay. Now, with linear factors, especially non-repeated linear factors, this is the easy way. Pretty easy way. Now, what that means is I can rewrite this integral then as two integrals. The integral of negative 1 over x minus 2 plus the integral of positive 1 over x minus 3. Remember, we had a over x minus 2 and b over x minus 3, and a came out to be negative 1, and b came out to be positive 1. So this is negative the natural log of x minus 2 plus the natural log of x minus 3 plus c. And I'm really fine if that's the way you want to leave it. Your book may combine these natural logs. You know, the natural log of the difference is the quotient, so this could be the natural log of x minus 3 divided by x minus 2, or, you know, natural log of a product if you end up with both positives. You know, you can use your log rules to rewrite them. But the whole key was, by rewriting this in this form where I have linear factors, I know the antiderivative of every linear factor is just the natural log. Which brings up to that point, huh? This is another one of those integrals I'm going to let you use. This is a Usubstitution idea. So rather than make you do a Usubstitution every time you come across the linear factor, I'm going to let you do this. Now in our case, that one I just did, the constant was, a here was 1. So I just end up with a natural log of the linear term. But you can use that antiderivative as you wish. Okay, so why don't you guys try to rewrite this one. So rewrite it as the sum, factor the denominator, then figure out what the numerators have to be for each of the separate terms. See how it comes out. Yes.
What was that integral we can use? Would you put that back up? Yeah, wrote it down.
You know, let me do the special case too. If a is 1, so if this becomes 1 over x plus b, you just get the natural log of x plus b. You know, that's a special case where the leading coefficient is just 1, which it often is on some things that you're going to factor. So you can. Is that okay?
Yeah, thanks. I see what.
No, I just want to get back to my problem here someplace. So you should be able to factor x squared plus 4x plus 3 into x plus 1 times x plus 3. And so you end up with rewriting x minus 1 over x plus 1 times x plus 3 equals a over x plus 1 plus b over x plus 3. When you multiply everything by the common denominator, on the left you're just going to get what the numerator was. And on the right you end up with a times the other denominator plus b times the denominator that was under a. So you end up with a times x plus 3 and b times x plus 1. Now the technique I showed you that I typically use is, when I can, is let x equal the number that makes this factor go to 0. So if x is negative 3, then I get negative 4 is, and when I plug negative 3 in for x, this becomes, the x plus 1 becomes negative 2. So negative 2b is equal to negative 4, so b is 2. Then I do the same thing with the other factor. Let x be negative 1. Negative 1 minus 1 is negative 2 on the left side. X plus 3 becomes 2. So I get 2a equals negative 2, so a is negative 1. And then I put those back up. So my fractions, rational expressions, become negative 1 over x plus 1 and 2 over x plus 3. Is that okay? And then we just have to take the, is that okay with everyone? Then we just have to take the antiderivatives of each of those separately. So you get negative the natural log of x plus 1 plus 2 over the 2 times the natural log of x plus 3. And like I said, depending on the program that they use, this could be written as natural log of x plus 3 squared over x plus 1. Just using your log rules. You can bring the exponents in and you can combine them, so you end up with something like that. Now, I'm really just fine with that first one. But, like I said, sometimes they rewrite the logs. Again, on tests and quizzes, I am going to want to see some of the algebra, but I do want to show you what your calculator can do for you, especially if you get stuck. So, you guys can see it okay. Make this brighter. Let's try as bright as it gets. That's better. Yeah, that looks better. Under the algebra menu, they have solve, they have factor, and they have expand. You can choose either 2 or 3. I chose expand, and I used it to do, so it did both those steps for me. Not only did it factor the denominator, but it figured out what b and a were. So it can do that as far as, so I just did expand, gave it the rational expression, and what it did was it wrote it as 2 over x plus 3 minus 1 over x plus 1. Or like I said, you could, just have used it to factor if you needed x squared plus 4x plus 3. And it'll factor that for you. Of course, it will also integrate if you want. So you wouldn't need to even do, if we do F3, the second one is to integrate. You just have to tell it what variable to integrate with respect to. And it doesn't put an integration constant, and like I said, it throws all that stuff together in one natural log, which isn't always the form that you would think of it. Okay, but it's a good tool to help you in those situations, especially sometimes with factoring, it can be tricky. All right, that was case 1. linear factors that aren't repeated. Case 2, we're still looking at linear factors, and when I say linear factors, this is for the denominator, and some of them might be repeated. So, an example, I have 5x squared plus 20x plus 6 as my numerator, and in my denominator, I have x cubed plus 2x squared plus x, which factors into x times x plus 1 squared. So again, I'm going to go off to the side, and we're going to try and rewrite these. Now the way these terms go, the linear term still a over x. And the first term, or the one that's repeated, is the same as it would have looked. So I'll use b over x plus 1. But then we're going to have another term. Now there's a couple ways to do this. The way your book does it is c over, and then you write the squared term. And if it were a cubic, I'd have d over x plus 1 cubed. So for a repeated root, you need two terms. One that's over the linear term by itself, and one that's over the linear term squared, the repeated linear term. So in this case now, when we multiply everything by this common denominator, the left side still ends up being the numerator. The right side, for the a term, I get x plus 1 squared. For the middle term, I get x times x plus 1. And for the last term, I just get x. And let's see if I didn't give myself as much room as maybe I wanted. Let me show you how that worked. And the first one, the x cancels. The second one, just one of the x plus 1's cancel. And on the third one, the x plus 1 squared cancels. So here I have a times x plus 1 squared. A times x plus 1 squared. Here b times x plus 1 to the first power. And here it's just c times x. So in this case, well, I'll still do the other one. I'll still do the other way. So let x equal, say, 0. If x equals 0, the left side becomes 6, and the right side becomes a. B times x here is going to go to 0, c times x is 0, so then a is 6. The other term I can use is I can let x equal -1. I stick -1 on the left side. It's going to take me a minute, so I might have to write it out here first. but the a term is going to be times 0, the b term is going to be times 0, and the c is times -1. So here I get 5 minus 20 plus 6, which is -9, equals -c, so c equals 9. I have a slight problem here now, though. Are you okay with what I did so far? I still have another constant. I still have to figure out what b is, but I used up all the values of x to help me cancel out factors. So just pick another easy number to plug in. And at the same time, we're going to substitute in the values we know a and c have. So that's why I circled these. So what's another easy number to plug in? I mean, and you can pick anything you want, but I'll pick 1. I already used 0. That's my favorite. And -1. So I'll let x equal 1. When I plug 1 into the left side, I get 31. When I plug into the right side, again, a is 6. So I have 6 times 2 squared plus b times 1 times 2. And c is 9. So 31 equals 24 plus 2b plus 9. 2b equals -2. So b is -1.
And you just picked 1 because it made it easy.
Yeah, I mean, you could have picked pi, but pi is not as easy to, I'd have to use my calculator to solve it. You can pick anything you want. So again, if your favorite number is 2, that's not much harder. You can plug in 2. I tend to avoid negative numbers if I can because, when you're squaring things and the signs get in the way sometimes. But 0 and 1 are by far my preference as choices if I have them. Okay, 6, -1, and 9. So that means this integral becomes the integral of 6 over x plus the integral of -1 over x plus 1 plus the integral of 9 over x plus 1 squared. Okay, which means I have another integral that I have to be able to do, and that maybe you guys are going to want to have. This is just 6 natural log of x, and this is negative the natural log of x plus 1. What's this one going to be? So let me go off the side here for a second. I'm going to do this as a general integral because we have this come up. So what's k over ax plus b squared? Gonna be. I mean, I guess I could even do it to the nth power. Well, we're going to do this with a u substitution. If u is ax plus b, du is a dx. So I pull the k out. This becomes u to the minus 2. In order to get up the a dx, I need to put an a inside. It means I need a 1 over a out front. have k over a times u to the negative 1 divided by negative 1 plus some constant. So it's negative k over a. Well, I guess I'll do one more step. Negative k over a u plus c, which is negative k over a, and u was ax plus b. Funky looking x. So again, in the special case, when the coefficient on x is just 1, I just get negative k over x plus b. So these would be other ones that I would allow you to have. And it means this one comes out to negative 9 over x plus 1. Okay. So let me let you guys try one. Okay. So first again, you're going to factor the denominator. In this case, it comes out to the product of x times x minus 2 squared. So we have this repeated linear factor. So we're going to rewrite this as something constant over x, a over x, b over x minus 2, and c over x minus 2 squared. You go through the steps of solving this, multiply by the common denominator, let x be 0 once, let x be 2 once to figure out to let the factors all be 0. You can figure out a and c that way. And then you have to choose another value like x equal 1, and you can solve for b. So I got a is negative 1, so it's negative 1 over x, 2 over x minus 2, and 3 over x minus 2 squared. Like that. Now each of the linear terms are going to give you natural logs when you integrate them. This linear term squared is going to give you negative 3 over x minus 2. Negative sign, and the denominator goes from being 2 squared to just the first power. Questions at all about that? You doing okay? Yes.
I didn't see how that last integral that you said we could use, how to plug that in.
So it's only this squared one here.
Right.
Somewhere in here. So if I have something over a linear term squared, the k over a is the coefficient on x, and k is the constant on top. I end up with negative k over a times the linear term just to the first power. In a special case where a equals 1, it's just negative k over x plus b. So in this case, k is 3, and so it becomes negative 3 over x minus 2. Well, those are good questions. Okay, so now, case 3. Okay, case 3 is some quadratic factors, but none of them are repeated. And when I say quadratic factors, I mean the ones that are irreducible. You're not going to be able to break them down at all. So this is partially factored already. It has x squared minus x and x squared plus 4 in the denominator here. The x squared plus 4, this is the quadratic factor that is irreducible. But the x squared minus x I can factor. Into x times x minus 1. Times x to x squared plus 4. So again, I'm going to go off to the side here and try to rewrite my rational polynomial. So I'm going to have an a over x, just like before, a b over x minus 1, that's also like before. But here, over my quadratic term, we're going to have a linear term. That means I need a cx plus a d. If I multiply everything by the common denominator, I get 2x cubed minus 4x minus 8 on the left. On the right, it's a lot more complicated. I have a times x minus 1 times x squared plus 4, and b times x squared plus 4, and I have cx plus d times x minus 1. Now, I could still use the same factoring that I did before, but I'd have a couple of different times I'd have to substitute in. Besides, I could substitute in 1 and I can substitute in 0, and those would help me. But then I'd have to sub in a few other ones. But I'm going to do it another way. I just want to make sure that I don't change the way that the book chose to do that here. Okay. So I'm going to expand this out. Just to show you the other way. Now this x minus 1 times x squared plus 4 is x cubed minus x squared plus 4x minus 4. So I have ax cubed minus ax squared plus 4ax minus 4a. And x times x squared plus 4 is x cubed plus 4x. And I only have b times all of that, so b times x cubed plus 4b times x. And here x times x minus 1 is x squared minus x. So I'm going to have cx cubed minus cx squared plus dx squared minus dx. That's a long one. Can you guys see that okay? It's a little blurry. That's about as. I'll try to write bigger. Okay, now the other technique, instead of substituting values of x, is based on the theory that every coefficient of each power of x has to be equal. So if I look at just the x cubed terms, I get that 2 has to equal a plus b plus c. Then if I look at the x squared terms, well, there isn't an x squared term on the left. So 0 would equal negative a plus b minus c plus d. So this one again was x cubed. Then I do x squared. Now I'm going to do x terms. So on the left I get -4.
Yeah, we're doing B.
Oh, I'm sorry. Just because I was looking at this one. Should only be the ones that are circled there. Thank you. So now when I do x terms, I get -4 plus is equal to 4a plus 4b minus d. Now for the constant terms, I have -8 is -4a, and that's it. So we have a system of equations, 4 unknowns, a, b, c, and d, 4 equations. Probably brings back memories from classes before. You can use substitution techniques, elimination techniques. If you know how to use matrices, you can use matrices to solve this, whatever you want. This last one, I can tell from this last one that a has to be 2. If I substitute that into the other ones, I get 0 equals b plus c, 2 equals -c plus d, and -12 equals 4b minus d. Then I can choose to add whichever one. Suppose I add these last two. I'm going to use elimination-like techniques. If I add these last two, I get -10 equals 4b minus c. I added them just because the d's were equal and opposite in sign. Now I can take that and add the top one. So -10 equals 5b. So b is -2. And if b is -2, I can substitute that into this one. So 0 equals -2 plus c, so c is 2. I can also substitute into the one up here. So -12 equals 4 times -2 minus d. So d equals 4. Lots of algebra. Nothing really having to do with calculus. Okay. Now, as I said, on a test, there's going to be probably one where I'm going to want to see all this work done out, but not probably on something as complicated as this one. So when you get to ones like this, feel free to use your calculator on. I'll tell you again on the test which one I want to see. But so I would want to see from here to this next step, but I wouldn't necessarily need to see this page worth of work. Okay. But we have A is 2, B is -2, C is 2, and D is 4. So A was 2, so I have 2 over x. B was -2, so I have -2 over x minus 1. And then C was 2 and D was 4, so I have 2x plus 4 over x squared plus 4. Now, actually, even though I wrote this one like that, I'm going to want to break that one into two integrals. Now I'm going to take these two separately off to the other side and do them. Now, typically when I do this one here, I don't necessarily want to break it up into the x term and a constant term. In this case, I do though. I'm going to use a u substitution on this one. If u is x squared plus 4, what's du going to be? 2x dx, and that's what I have there. Okay. So you really want to do is you want to break it up into a numerator that represents the derivative of the denominator. And then over here, whatever's left. Okay, so you're going to use the 2x plus some constant sometimes. So if this had been x squared plus 4x plus c, for instance, then I'd need a 4. I would need the 4. Okay, but in this case, I don't. All right, so let me do those. So the first one was the 2x over x squared plus 4. If I let u be the x squared plus 4, du is 2x dx. This ends up being the natural log of u, which is the natural log of the x squared plus 4. If I do the integral of 4 over x squared plus 4, this one is the one we just did from last night's homework. I have an x squared plus a constant, so we're going to let x equal 2 tan theta. X squared plus 4 then is going to be 4 secant squared theta. dx is going to be 2 secant squared theta, d theta. So I'm going to use the 4 secant squared as my denominator. 2 secant squared theta, d theta is what dx ends up being. I just have that extra 4 there. So I'll pull the 4 out front. I guess I could have left it somewhere. I end up with a half on my coefficients times the 4 out front, so I end up with 2 times integral of d theta. Secant squareds cancel. So this is 2 theta plus c. Theta is the inverse tangent of x over 2. Alright, so I'm going to put all those together back here. So this one's 2 times the natural log of x. Negative 2 times the natural log of x minus 1. The 2x over x squared plus 4 ended up being the natural log of x squared plus 4. And then this one ended up being 2 times the inverse tangent of x over 2. it's very possible that either in the calculator or in the answer in the back of the book, they're going to put these logs together. The 2's are going to go in as squares, so it's like the natural log of x squared times x squared plus 4 divided by x minus 1 squared plus 2 times the inverse tangent of x over 2 plus c. What do you think? Still okay? Just a lot of work? Did you have a question? Okay. There's not much time left, so I'm just going to write down the situation when there's a repeated quadratic. So I might have something like this. So I have 8x cubed plus 13x over x squared plus 2 squared. So this is a quadratic term because it's x squared plus 2 plus means it's not reducible, and squared. So when I try to rewrite this one, what you're going to do is you're going to have one set of linear terms, the ax plus b over x squared plus 2, and then another set of linear terms over that quadratic squared. So as I mentioned, once you get to this one, I'm expecting you, I'm fine with you. If you have the time and you want to go through and solve that, that's great. But if you don't, when you get to the ones this complicated, use the expand idea from the algebra section, algebra tab, and it'll rewrite this as 8x over x squared plus 2 minus 3x over x squared plus 2 squared. And then you can do these integrals. And again, actually in this case, it's just going to be a natural log, and this one is, both of these are going to be used substitutions. They're not going to have to be the